Bismillahirrahmanirrahim. So this is the second part of the fifth lecture of statistics and probability theory. We were discussing the properties of arithmetic mean, and the first property, which was the sum of deviations from its mean is always equal to 0, was discussed in part 1. In this part, we will start with the second property of the arithmetic mean, which says that the sum of squared deviations of the exercise. Remember that in first part in which we have discussed the first property, it was written there that the sum of deviations from its mean. Now it is written here that the sum of squared deviations of the exercise from the mean x bar is a minimum. In other words, if we take the deviation of each observation from its mean, then we square them and then we sum over them, and we take some other arbitrary value which is other than the mean, take their deviations and then square them, and then find out the sum over them. The sum of deviation from its mean and then square is always minimum, rather than if a is some arbitrary value, and whatever the value of a is, it should be other than the mean, and this particular value always should be greater than equal to this thing, which is sum of square deviations from its mean, and they both will be equal if and only if a is equal to x bar. Otherwise, this term, which is summation x minus x bar whole square, is always minimum. Whatever you take the value of a, either it is greater than mean, which is x bar, or it is lesser than mean. In both cases, this deviation will be minimum. We can prove this mathematically. As you say that this is summation xi minus a whole square, which is equal to, we have added and subtracted the mean, that is, we are adding and subtracting the same term. So this is mathematically justifiable. Now this is x minus x bar plus x minus a, and this one is the whole square. So what we can do, we can use the formula of summation. Let's suppose, if you remember the formula c minus d whole square, this would be equal to summation c squared plus d square minus 2c d, 2 times c into d. So as there is c is equal to x minus x bar, d is equal to x minus a, so this is equal to x minus x bar whole square plus x minus a whole square plus 2 times x minus x bar plus into x minus a. So by applying summation inside the bracket, you will came up with these terms, which is summation x minus x bar whole square plus 2 times x minus a, as this is constant, x bar is also constant, and a is also a constant, so this would be outside the summation, and we will apply on summation on the variable term, which is x minus x bar, plus there will be summation x minus a whole square, and as this is the constant, so this summation will become n, as already we have discussed in previous part. Now what we have left with summation x minus a x bar whole square plus 2 into x bar minus a into summation x minus x bar. So by the first property, which is the sum of deviation of each observation from this mean is always equal to 0, which is this. So by applying this property over here, this whole term will become 0 and you will left with summation x minus x bar whole square plus n into x minus a whole square. So you have seen that this is the sum of squared deviation from its mean, and whenever you will add some squared term in this, it will be equal to summation x minus a whole square. So both of these sides will be equal only when this squared positive term will be added in this term. So it is obvious that without this term, summation x minus x bar whole square will be lesser than summation x minus a whole square. So by applying this, we come to know that whenever you take the deviation from its mean and square them, then you take the sum over them, it will always lesser than whenever you take deviations from some arbitrary number and then sum over them and then take summation over them. This term will be lesser than this term. This property is usually called the minimal property of the mean. So you can also say that this is the minimal property of the mean. Third property. If k subgroups of data consisting of n1, n2 till nk, where summation ni is equal to n, observations have respective means x bar 1, x bar 2, x bar k, then x bar, the mean of all the data, is given by x bar is equal to n1 into x bar 1 plus n2 into x bar 2 up to so on nk into x bar k whole divided by n1 plus n2 till nk, which will be equal to summation ni into x bar I divided by n. What this property is saying that, let's suppose we have a data which have n observations and we have divided these n observations into subgroups. Let's say we have n1 observation in the first group, n2 observation in the second group, and 3 observations in the third group. The mean of first group is x bar 1, second group is x bar 2, third group is x bar 3. So the combined mean of all these subgroups is, which is usually denoted by x double bar, here we should have x double bar, which is equal to n1 into x bar 1 plus n2 into x bar 2 So their combined mean can be found out through this way, and this could be extended into k subgroups as we have discussed in this term. Here we have taken only 3 groups to describe the whole scenario. So this could be written in this way: summation I is equal to 1, 2, 3 Ni into x bar I divided by n, as n1 plus n2 plus n3 will be equal to n. Example: the mean height and the number of students in 3 sections of a statistic class are given below. There are 3 sections A, B, and C, and number of boys in each class is 40, 37, and 43, and their mean height is 62, 58, and 61. Find the overall mean height of 120 boys. If you sum over all these number of boys, it would be equal to 120. And this is basically n, total number of boys. This is small n, 1, n, 2, as these are these A, B, C are these subgroups, and n. So you can find out the overall mean, or you can say it combined mean by x double bar is equal to n1 into x bar 1 as n1 is 40 and x bar 1 is 62 plus n2 is 37 and x bar 2 is 58 plus 43 into x bar 3, which is 61, whole divided by 40 plus 37 plus 40. This would be equal to 60.41, which is the overall mean height of 120 boys.